So we humans are sort of the ultimate seat of those elements of consciousness, in your view. Is that right?
Oh, not at all. We're probably among the less sophisticated ones.
So what's an example of a more sophisticated one?
Well, our headset has only got 4 dimensions. Why not have consciousnesses that are using headsets with a billion dimensions?
But I mean, but then I'm a little surprised, so do you view our if you imagine, so first of all, do you believe there are laws of physics, for example? Or do you believe that there are, in other words, are there things that are laws on top of which our brains and the electrochemistry of them and so on operate? Or do you think that it's sort of, is there some substrate underneath? Or are you somehow imagining that your scientific theory is built? I mean, okay, for example, we could imagine that you never had a theory of physics. All you had in physics was a collection of experimental results. And you would have a bunch of, you could even imagine sort of axioms about how, I've seen that this thing correlates with that thing. And we would have this kind of observational version of physics that never had anything sort of underneath. I'm just curious, how do you imagine kind of the nature of kind of what's happening in brains relating to sort of the substrate or the potentially laws of physics?
Right. So my view is very, very similar to what some high energy theoretical physicists are doing right now, which they're looking for new principles and structures beyond space-time. So this is Nima Arkani Hamed and a bunch of other people. There's the European Research Council just announced the Universe Plus project and putting 10 million euros into what are called positive geometries beyond space-time and beyond quantum theory. So what they just had their first workshop in February, where they brought together about 100 PhDs in mathematics and theoretical physics. What they've discovered are these new structures beyond space-time called positive geometries, amplitude-hedron, associahedron, cosmological polytopes, that their volumes encode scattering amplitudes.
Yeah. I used to do particle physics when I was a kid.
I know.
These things are a bit more recent than that. But I mean, I think the thing to understand about sort of particle physics and where it's gone is, I think what you're describing is kind of the limit of what one can view as the S-matrix approach to particle physics. I mean, the one view of what happens when sort of particles interact is you see all the details of what's happening and the mechanism of the interaction. Another approach that Heisenberg introduced was just this: we don't know what's happening inside. We're just going to say, what are the things that are coming in? What are the initial states? What are the final states? And we're just going to define this thing, we call it the S-matrix, that sort of describes the transformation from initial states to final states without having to address this question about sort of the mechanism of what's happening inside. A thing that I learned recently is a piece of history of science trivia, but it's interesting to me at least, is about how Heisenberg ended up coming up with the S-matrix.
Okay.
So one of the things that's relevant to, my efforts to understand fundamental physics is the question of, what's discrete, what's continuous. Back in antiquity, people were arguing about everything, is matter discrete or continuous and so on. That finally got resolved at the end of the 19th century, basically. And yes, matter is discrete, it's made of molecules, we can see Brownian motion, all those kinds of things. And then very soon after, light is consistent with being thought of as being discrete. At the time, 100 and something years ago, most of the obvious physicists were convinced that space was also discrete. But they kept on trying to make that work from a mathematical point of view, and particularly make it compatible with relativity, and they kept on failing. And Heisenberg, as I recently learnt, was kind of in the middle of that whole effort when he said, I just can't make this work. And he said, forget it all. I'm not going to try and describe the mechanism. I'm not going to describe what's happening in space. I'm just going to set up the S-matrix and say, this is, given this initial configuration, how will that translate to final configurations? So I think, it is certainly possible to in terms of what we experience in the world, there's no question that you can describe our experience of the world just in terms of kind of the initial states, the final states. You can describe just, as I was mentioning, sort of an axiomatic physics where all you describe is what relates to what, and you don't really talk about what the underlying substrate, the mechanism of physics is. I think that's and it's interesting, in our models of physics, at some level, that's what's happening. At some level, what really matters are things like causal graphs that say how, one event relates to another event. The question of what is how are those events kind of, when we start setting up things like space and time are very different in our kinds of models. Right. But when we sort of say, this is a lump of space, that's something which is something we can do as a convenience for understanding what's going on. But ultimately, in terms of our experience, what matters is this causal graph of relationships between events. So I think, in that, so I'm certainly on board with the idea that what matters to us is just this causal graph of events. Now, whether that means, and for example, the very construction of space, for instance, is something that I view as being kind of a coincidental feature of our scale in the universe. That is, the fact that we say there's a state of space at a particular moment in time. Yes, I look around this room, it's, I can see maybe 10 meters away. Light gets to me in a microsecond from 10 meters away, but it takes me milliseconds to process what I saw. And so I've kind of integrated this whole, I've aggregated all those photons that are coming in, and I can reasonably say there's a state of space that I can talk about, and then that might change over time. Whereas if I was, for example, if I thought a million times faster than I do, then, I wouldn't probably integrate space and I wouldn't talk about space. And if somebody told me, oh, by the way, there's this way of thinking about the physical world that involves the idea of space, I'd say, well, that's kind of interesting, but it's not necessarily something that is relevant to my particular way of observing the world. So I think that's I don't disagree that the construction of space is a feature of certain details of us being the way that we are, so to speak.
I agree, and that seems to be what the this universe plus the positive geometry approach to physics is after as well. One of their banners is they say space-time is doomed. It cannot be fundamental because it ceases to have operational meaning beyond the Planck scale. So they're actually looking for new foundations for physics entirely outside of space-time and remarkably, entirely beyond quantum theory. So these new structures, for example, have no Hilbert spaces. And they're saying there are no Hilbert spaces here. There is no unitarity, and so forth. This is beyond quantum theory. But they want to get space-time and quantum theory emerging together from things like the amplitude-hedron and so forth.
Yeah, I'm not sure that's the best way to do it. I think one of the things, I have to say, I did physics when I was much younger, and then didn't do physics for a long time, and then kind of got back into doing it when I realized that a bunch of things that I'd figured out for other reasons were sort of converging on giving us a view of how physics might work. And it's been super exciting to me to actually, I think we got it. I think we know how it works. And I think Nima and folks like that, I know something about what we've done. But I think that the paradigm it's interesting because the paradigm is a bit different from traditional mathematical physics, but there are very beautiful connections to lots of work that's been done in traditional mathematical physics.
Sorry, just a moment. The paradigm of space-time is doomed, or the paradigm of the amplitude-hedron?
No, the paradigm of what people call Wolfram Physics Project. It's something where sort of the foundational machine code is very computational. What that turns into at the level of things that we can do experiments on and so on is sort of looks much more like traditional mathematical physics. And what's really cool is that a bunch of limits of our model clearly are kind of map into things that have been studied in traditional mathematical physics. And that's kind of what you would hope would be the case, because, what we're trying to do is deal with something that is sort of a lower level machine code of the structure of the universe, the structure of reality, basically, than than the things, I'd always thought of what I was doing as kind of going underneath space and time to something which is sort of more fundamental than space and time. I mean, I think it has not helped the progress of a lot of kind of physics, that people have sort of had this idea that space and time are the same kind of thing, which is kind of, I think, in terms of doomed ideas, that is a doomed idea. That was a thing that, Einstein didn't have that idea. That idea came in when Minkowski said, it's really cool that there's this quadratic form that we can write with space pieces and a time piece, and they all sort of fit together. And that's how kind of this concept of space-time was born. And I think it's sort of a mistake, because I think that, time, as I see it, is this kind of progressive application of computational rules, and space is this thing that you can reasonably construct as a way to describe what's in the universe. It's kind of the structure. There's sort of a data structure of the universe that you can slice into pieces of space. You could slice it into quite different things as well. And I think it's a feature of observers like us, I think, that we believe in space. I mean, it's the same thing that, the fact that we believe in fluids, as opposed to just saying they're all a bunch of molecules bouncing around. That's a feature of observers like us, and not necessarily a feature of all observers. I mean, I do think, by the way, in terms of dimension, you mentioned, is 3 + 1 dimensions kind of the fundamental thing? I'm sure the answer is no.
Right.
And, my guess is that there is some totally obvious feature of the nature of the observations that we make that leads us to believe that the universe is 3 + 1 dimensional. I mean, in terms of sort of the computational kind of representation of the universe, it really doesn't make much difference that it's 3 + 1 dimensional. We could as well be, exploring it on some one-dimensional space-filling curve or some such other thing. It's, I think I'd love to know what feature of us makes us believe that it's 3 + 1 dimensional.
Right. Right. So you have your Rulliad, right, which is all the possible different computational rules, and our projection of that Rulliad into 3 + 1 dimensional space-time is just one of an infinite number of different projections you could take, right?
Yes, indeed. I think the thing that has been very exciting to me, and was not something I saw coming at all, was the way in which one can, given the idea of the Rulliad, the way in which one can derive the known laws of physics. And that's something that, if you'd asked me 5 years ago even, would there be a way to derive general relativity, derive quantum mechanics? I would have said, well, there might be an underlying theory from which those emerge, but I don't think that there would be any way that would make those theories necessary. Those are theories which just happen to be the way they are because the universe happens to be the way it is. If you'd asked me about the second law of thermodynamics, for example, I would have said, as people have said for 100 and something years, that, it's probably derivable in some way, but we don't quite know how to do it. But the thing that's been super surprising to me is that general relativity, quantum mechanics, and it turns out the second law, all seem to be derivable. What's the assumption that you need to derive them? Well, the Rulliad doesn't really have assumptions. The Rulliad is just this abstract thing that you set up. The assumptions have to do with what kind of observers we are.
Right.
And, it seems like there are two critical assumptions, although I'm guessing that there are actually more assumptions that I haven't correctly identified yet. But the two that I have identified is, we're computationally bounded. We don't get to trace every detail. We only get to notice certain aggregate things. And we believe we're persistent in time. We believe that, which is something I'd be really interested to talk about, is kind of the, to me, it seems like a crucial feature of observers like us is that we have this persistent thread of experience. We don't, and we have a single persistent thread of experience. It's not the case that we kind of are, have our multiple thoughts kind of branching out in all possible ways, nor is it the case that we are sort of here just for a moment, and then it's a different us at the next moment. We kind of have this perception, at least, that we have a sort of consistent thread of experience.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for Toe Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.